Hello everyone, now let's get started for the first lecture of this class, Advanced Large Language Model Agents. I'm Xinyun Chen, I'm a research scientist at Google DeepMind, and I'm instructing this course with Professor Dong Song here at UC Berkeley and Kaiyu Yang from Meta. We also have an amazing TA team who help us a lot on sort out the cost logistics with the head TA Alex and readers Tara, Ashwin, and Jason. Last semester, we launched the first version of this LLM agents course, both here at UC Berkeley and also on MOOC. Last semester, we had a very amazing line of guest speakers talking about very broad topics about LLM agents. So we discussed about the fundamental reasoning techniques, the agentic workflows, and different applications, etc. We had around 15,000 people registered on MOOC. We also launched a hackathon, which attracted around 3,000 people participating globally. And we are very grateful for this generous sponsorship from our industry partners who gave us around $200,000 support in prizes and resources. We will announce the hackathon winners very soon, so stay tuned. Now let's go back to LLM agents. So the core of a large language model-based agent is that the kind of the brain of this agent is a large language model, which is going to perform reasoning and planning to take action at each time step. Then with this action to interact with the environment, it will receive the feedback and revise its internal memory so that it can better plan for the next step to take. So with this agentic framework, it allows the LLM to also utilize this external feedback and tools whenever available, so that it can further expand its capability and to get more informed decision in its own decision-making process. So some common components in the agent framework include tool use and retrieval. Then why do we want to empower these large language models with the agent framework? Because solving real-world tasks typically involves a trial and error process, especially when we deploy this LLM agent in a new environment. It really needs to interact with the environment to understand some success and failure modes in different actions, so that it is able to revise its own internal memory. At the same time, leveraging external tools and retrieving from external knowledge further expands LLM's capabilities. And with the more with this agentic workflow design becomes more mature, it also facilitates the accomplishment of complex tasks. This includes task decomposition, allocation of subtasks, division of labor for collaboration between different specialized modules, and multi-agent generation. Many people are saying that this year, 2025, will be the year of agents. So nowadays, we have already seen the explosion of LLM agents for various applications. And in many domains, actually, these LLM agents transformed how previous people are thinking about what these how these AI models can behave. So some very successful demonstrations and also practical use cases include code generation, computer use, personal assistant, and robotics. And this list of applications will keep growing in the future as well. And also there are some domains like education, finance, etc., where we already have seen an emergence of pretty nice LLM-based agents. Another factor that further drives this excitement about LLM agent development is about this recent rapid progress of reasoning models, starting from September last year with the release of OpenAI o1. And starting from that model, we have also seen a lot of great reasoning progress during the meantime. For example, last month, we saw the release of the Gemini 2.0 flash thinking model, and also the OpenAI o3 model. And this month, we saw the release of DeepSeek R1 and Kimi K1.5. And also within the same model series, we can see a very drastic improvement from different versions of the model. So for example, there is a rapid progress of performance from OpenAI o1 to o3. And also, if we compare the current Gemini thinking model to our initial version released last month, there are also a lot of improvement we can see. And if we think about this progress in reasoning, the most impressive performance we have seen so far are in math and coding, especially for solving those very challenging problems. For example, last year, with the alpha proof and alpha geometry system developed by my colleagues at Google DeepMind, they received the silver medal or nearly gold medal performance in IMO last year. And also with the more recent OpenAI O3 model, it shows that it can be ranked among top 200 among the human participants on Codeforce's competitive programming contests. If we think about these milestones, probably they are even very hard to imagine a couple of months ago before they actually happen. So for this semester, our course is called Advanced Large Language Model Agents. So we will do a deeper dive into the methodology part, especially on the reasoning techniques. So we will talk about fundamental techniques for inference time scaling, training techniques, and also search and planning. And for the application side, we will focus more on software engineering and mathematics. So this includes code generation and verification, and also auto-formalization and theorem proving. After this deep dive on the methodology, we will talk about LLM agents use cases for real-world enterprise application, and also more advanced agentic workflow design, and also topics about safety and ethics for real-world deployment of these LLM agents. Now I will hand over to our head TA, Alex, to talk about cost logistics.
Okay, so the course is pretty similar to last week's, last semester's. The main difference is we are moving the lab to a later due date. So last year, the lab was a bit earlier and it was so much shorter. This semester, the lab is going to be more involved, and it will be it will be released later and you'll have more time to work on it. The other main thing, apart from not having a hackathon, is we're also going to sort of open up the project. So last semester, the project was sort of open-ended. This time we'll have 2 tracks, an applications track and a research track. I think I wrote about it here. So the applications track is pretty much the same content as last semester. The research track is new. Basically, if you want to or are interested in submitting a conference publication or a workshop publication, you can apply to the research track. We'll have a Google form out shortly. And if we select you, then you can sort of work with under the supervision of like some of Don's postdocs and grad students to basically try to submit a workshop paper for this class. Other than that, everything else is sort of the same as last year. I would just refer to the final, like everything is on this master website, and we won't be having a syllabus, just keep track of the changes on here and on EdSTEM. So that's it for logistics.
Yeah, and also like same as last semester, we will also invite like a very great like speakers to talk about different topics of advanced like LLM agents methodology and applications. So we are still finalizing the guest speaker schedule. So also check out this course website for the most up-to-date information. In this lecture, I will talk about inference-time techniques for LLM reasoning. So in the intro of the course, we briefly talk about this like advancement of reasoning models, which is kind of one of the highlights of large language model development in last year. And so here I will like go more into details about what we can see from these reasoning models. So on the slides, I'm showing these results, which was like quoted from the O1 blog. So from here, we can see that actually OpenAI O1's model started to achieve pretty impressive performance across various very challenging tasks where previous models are really struggling with. So this includes the competition level math problems like in the Emmy contest last year, and also competitive programming contest on Codeforces. And in the recent like O3 results, they further show this like the performance can further improve with more inference time compute. For example, here I'm showing these like curves they demonstrated on a benchmark called ARCAGI. So this is a benchmark that includes a bunch of puzzles to test how well humans or AI models can learn some reasoning patterns given the demonstration examples. So this was a very challenging task. So for those existing models before O1, if we do not apply any special inference time techniques and just do the like very regular inference, then all existing models can achieve like a less than 25% accuracy. Even with the O1 model, it can only achieve around 30% accuracy. But with the recent O3 model, if we set the inference time budget to around $20 per task, it can achieve a performance that kind of matching the average human annotators or mechanical turkers. And if we further scale up this inference time cost to a crazy number like $1,000 to solve one problem, then actually the model can achieve 87.5% accuracy. So definitely this is a very expensive way to solve this particular task, but it shows how this model can perform in the ideal case when we do not care so much about inference time compute. Then here on the slides, I'm showing a very simple like OpenAI O1 demo where basically I code the model to solve a planning problem. So what is different for this O1 model? So the main difference is that for the existing LLMs before the O1 model, when we enter a user query, then the model will directly generate this response. But in the O1 interface, they include this sort process. So and basically this process can take different amount of time depending on the difficulty of the task. For example, for the specific question I asked the model, it takes slightly more than 1 minute to generate the final solution. And in the O1 interface, they didn't show the row sort process. Instead, they show a summarized version of the hidden sort. So from this hidden sort for this specific planning problem, we can see that it summarizes some key stages in the reasoning process, including laying out an initial plan, evaluating it based on the model's internal belief, and then revise the plan so that it can satisfy the constraints and improve the optimality. Then with the Gemini 2.0 thinking model, we also make these sort tokens visible to users. So on the slides, I'm showing a demo where actually this question includes an image input. So this question is, the math part of this question is pretty simple. So basically, there are 4 balls in the image, and the question is asking the model to take 3 out of these numbers so that the sum is 30. So the sort here, as you can see, is pretty long. So after we enter the query, the model immediately generates these sorts. And we don't need to read the reasoning process token by token. I know it's pretty hard to read. But the most interesting step we can see from this multimodal query is that there is a, so at the beginning of this image, there's a specific number, which is 9. So at some point, the model figures out a very important step for this question. So because if you want to get a sum of 30, actually we need to turn this 9 into 6 by rolling this ball. So this is a very interesting feature of this query when we put these numbers on some balls. And also this step itself is not that kind of difficult mathematically, but actually it is an interesting trick. And if we earlier, if we do not allow the model to generate this long sort, this specific step will be very hard to figure out. And also, besides these models from OpenAI and Google DeepMind, there are other reasoning models out there recently. At the beginning of the lecture, I mentioned there are also models from the DeepSeek team and also the Kimi team. And out of all these breakthrough in reasoning models, one core shared idea is that we need some way to trigger the large language model to generate long chain of thought before it actually concludes with the final solution. And in the literature, there are different approaches to trigger this chain of thought generation. Like in the original chain of thought paper, they designed a future prompting scheme, which basically demonstrates this thought process in exemplars. And later on, there are some works showing that we can apply instruction prompting to achieve this. We can use the instruction, let's think step by step. And for the recent chat models, we can see that even if we do not give any special instructions to the model also tends to generate some thoughts before coming up with the final answer, no matter whether the thought is short or long. So there are different ways to train the model to achieve this, for instruction tuning, where we actually put this chain of thought data into our supervised fine-tuning mixture. And also, what we can see from recent reasoning models, we can apply reinforcement learning to achieve this goal. In this lecture, I will focus more on inference time techniques for scaling token budget. And in the future lectures, we will also dive deeper into reasoning techniques. And there will be some other guest speakers who will come here to share their thoughts. So for this lecture, I will discuss like 3 parts about reasoning techniques at the Inference-Time. I will first discuss the basic prompting techniques. And the common idea among these prompting techniques is that we want to allow the model to use more token budget to generate a single solution. Then in the second part, I will talk about techniques to perform search and selection from multiple candidates. And the common idea here is that we want to increase the width to explore the solution space. In the last part, I will talk about iterative self-improvement, will allow the model to increase its steps to reach the final solution. Then after all these discussions of different parts, we will also see how we can best utilize different combinations of these techniques to seek the best way to utilize the inference-time compute to improve the LLM reasoning performance. So let's get started on the first part about basic prompting techniques. Before we talk about more advanced prompting techniques, let's first review the background about standard prompting. So basically in standard prompting, let's say we want to solve a math problem as shown on the slides. Before the line of works on chain of thought prompting, the common practice is that we just put some question answer pairs into the prompt. Like here, the question is the math question and the answer is the final answer. So before the advancement in post-training techniques, if we directly apply this standard prompting, then the performance is pretty poor on reasoning benchmarks. The fundamental issue is that if we look at these standard future exemplars, they only provide information on the final solution format, but it doesn't tell the model about the rationale to derive the solution. Now we can imagine that if we are taking a class and the teachers basically just teaching you with the final official solution without any more context, then if you do not have relative background knowledge yourself, then it will make your teaching a lot more difficult. So for the chain of thought prompting, the idea is that we will include these future exemplars with thoughts. Again, let's take a look at this example of solving math problems. So here, instead, in the exemplars, we will provide these calculation steps to basically demonstrate the model how we should how we should derive these solution step by step to achieve the final answer. Then after giving these exemplars with chain of thought rationales, then the model is able to solve this problem correctly. In practice, how these models can benefit more from chain of thought prompting compared to standard prompting is also dependent on the model's fundamental capabilities. So here on the slides, I'm showing the scaling curves presented by the original chain of thought papers and also some other related papers about these chain of thought properties. So we can see that among different model families, one common trend is that this CLT performance improves more significantly with the increase of the model size. And in particular, if we look at this gap of chain of thought prompting versus standard prompting, then better models benefit more with CLT generation. And there is a drastic improvement on reasoning performance once the model reaches a certain scale. I also want to know that here for these curves, they are from papers in 2022. So these experiments are done using pre-trained only LLMs. So this is why it is important to apply some prompting so that the model can generate these thoughts immediately. And also with these recent post-training techniques, they might show some different scaling curves. Like we have seen some strong but very lightweight LLMs recently. But then the main conclusions will still hold. We will still see this overall trend. Basically, once the model becomes better, it will benefit more from this this allowance of the chain of thought generation. Then in the follow-up work called large language models are zero-shot reasoners, they further find that even with pre-trained only large language models, we do not have to provide the model with exemplars to elicit this CLT generation. Instead, we can achieve this with an instruction. Like in the paper, they demonstrate this instruction. Let's think step by step. Then after we apply this instruction, before we ask the model to generate the answer, the model can also generate some thoughts before generating the final solution. And empirically, they demonstrate that this zero-shot COT significantly outperforms zero-shot performance, especially on harder like math and symbolic reasoning tasks. So zero-shot COT is more convenient than few-shot COT in the sense that we no longer need to manually annotate thoughts ourselves as exemplars. But if we compare their performance, zero-shot COT performance is still much worse than few-shot COT. Then a very natural question I want to ask is, how can we get the best of the both worlds? How to improve COT performance without manually labeling exemplars? So this is what we want to achieve with our paper, Large Language Models as Analogical Reasoners. This paper was published at iClear last year. The idea is that instead of directly providing the model with exemplars, we instruct the model to first record relevant exemplars to solve the test problem. Then based on these like model-generated exemplars, then the model will try to solve the test problems as like just imagine that these self-generated exemplars are just some COT exemplars provided by external sources. The benefit of this design lies in twofold. First, these exemplars are self-generated by the large language models, so we fulfill our original goal. We don't need to do any manual labeling here. And on the other hand, because this instruction is applied to each test question, so basically for different test questions, the model is able to generate different exemplars which are more relevant to the concrete topics covered in the test question. So these exemplars are more tailored to individual problems. We call our approach analogical prompting because this methodology actually can be motivated by human analogical reasoning. If we think about few-shot prompting, it is not supernatural if we think about it in a human reasoning way, because humans are not explicitly given demonstrations every time for each single new problem. And instead, humans also intrinsically recall from past relevant experience. So in a classic reasoning methodology book called How to Solve It from Polya, they have a very nice description about this reasoning method named Do You Know a Related Problem? So the idea is that when solving a problem, we look for a pre-formally solved problem which is linked to our present one by generalization, specialization, or analogy, and want to learn from these like past results or their methods so that it can help us solve new test problems better. If we think about it from the human reasoning perspective, then besides exemplars, we can also instruct the model to generate some higher level knowledge, which can be like a more like better summary of what we need to solve the new problems. And this generated knowledge can complement the problems with broader insights. So here, let's take the solving coding problems as an example. So given a new coding problem, we can first like instruct the model to self-generate some knowledge, which is more of like higher level tutorial about the algorithms we need to solve the problem. And also the model needs to identify what are the main algorithms we need so that it can come up with related exemplar problems with their corresponding code. Then after this instruction, and also once the model generates this related like background knowledge, including higher level tutorial and exemplars, then the model goes back to solve the initial test problem. So in the results, we show that basically analogical prompting not only outperforms zero-shot COT, but it actually outperforms manual few-shot COT as well. And we show this performance improvement in like math problem solving, code generation, and also like big bench reasoning tasks. If you look at these results at the first time, you might be a bit surprised because note that here, all these exemplar problems or the knowledge are generated by the model. So intuitively, it might contain more errors than human annotated exemplars. And empirically, we indeed observe this trend. We see that, for example, for those like exemplars generated by the model for math problems, around 70% of them are accurate and also they are relevant. But the rest can have some like issues, like they are completely irrelevant or there are some actually wrong calculation steps. But even though there are some noises in the demonstrations, the model still benefits a lot from it. So given this finding, you might imagine that this means at least the model should be able to generate some reasonable exemplars, or otherwise it cannot learn from it at all. So based on this intuition, we also conduct a pretty rough a scaling study for this analogical prompting. So here we are comparing models among different, or among the GPT text model families. I know these models are all shut down and deprecated now, but this trend will still hold. So basically, we can see that weaker large language models benefit less from analogical prompting. Although if we compare the performance to zero-shot chain of thought, it still is on par or still outperforms their performance. And with stronger large language models, like starting from text DaVinci 002 in the GPT family, analogical prompting starts to outperform chain of thought prompting with manually designed exemplars. And notice that actually this approach can even outperform retrieved exemplars. So for retrieval method, what we did is that basically for each test problem, we implement a retrieval approach so that it will find those most relevant problems in this GSM AK math corpus training data. So one explanation here is that this generated chain of thought by the model can be more tailored to the underlying reasoning style of these pre-trained or instruction-tuned large language models. So this finding actually is also in line with the recent trend, like when we are trying to develop the reasoning models, instead of putting human written thoughts, we can have some training methods so that the model is able to discover the best reasoning strategies by itself. Now let's go back to the instruction. Let's think step by step. So why do we have to use this sentence? Is there something special about it? So in the original zero-shot COT paper, they conducted this ablation study of different variants of these instructions to trigger the chain of thought generation. So some of them do not make much sense. So it is kind of not surprising that they do not perform well. But if we look at those different instructions in the top category, instructive, if we mask out these accuracy numbers, it might be not that intuitive to know which instruction should be performed better. And it can be not very good to see that even if you just change a couple of words, then the accuracy number can change very dramatically. So this shows that current large language models are pretty sensitive to prompt design. And and also in many cases, there's no clear principle about how to write optimal prompts. And this is why nowadays there are still many people who are writing a lot of guidelines about how to have the best practice to do prompt engineering. So given this observation, a very natural question I want to ask next is how we can reduce this manual work for writing prompts. So one idea is that since our large language models can solve many challenging reasoning problems and also answer other queries, so why don't we also use it to help us do the prompt engineering or prompt design in general? So in the iClear 2023, there is a paper called Large Language Models are Human-Level Prompt Engineers. So the high-level idea is basically to apply a large language model to propose prompts, and so that we hope these model-generated prompts can also perform even better than human-written prompts. So here I'm showing the complete diagram of their method. So there are two important stages. The first is this proposal generation, where we can leverage this large language model to generate initial instructions given our task description. Then once the model generates different proposed prompts, then we'll score each instruction based on the prediction correctness on a small set of problems. So here, basically, we will hold out a small validation set, which can tell us the quality of each prompt. So here, the setup might be more similar to the traditional machine learning task where we have this separation of training and test. But actually, we do not need to include so many examples here for this validation purpose. Like in most cases, it is sufficient to include tens of examples or just around 100 problems. Then in our work published at iClear last year, we go further where we try to use this large language model, not only just to propose some instructions and do some kind of a search and mutation, we also want to apply it as an optimizer to iteratively improve the prompt. So the idea of our approach is that we want to instruct the LLM to leverage the past optimization trajectory represented as sorted solution score pairs so that it can learn to iteratively generate better prompts with more steps. So in this work, we frame it as a more general optimization framework in the natural language space. But in this specific use case of prompt optimization, basically this means that we will have two large language models as optimizers and evaluators. So basically, this optimizer is the large language model, which is responsible for proposing a new instruction given old ones and also the task exemplars. And the evaluator is the scholar, which will evaluate the accuracy or performance of a given instruction. Now let's take a look at how we can design the meta prompt to achieve this goal. So on the slides, I'm showing an example meta prompt for GSM-AK to solve the math problems. The prompt itself looks pretty long, but basically there are two main components. The first one is this trajectory, including the instructions we have explored in the past steps and with their corresponding accuracies. And in practice, we will sort them in the ascending order, and we can remove those older ones if the context length is not enough to put all of them in the history. And we also provide these exemplars to show what's the task we want to optimize. And basically here, for example, for math problems, we only need to include these QA pairs with the final answer. So again, there's no need to annotate any chain of thought or any explanations of how we can derive this solution. Then for the results, basically, again, we are testing all these instructions on pre-trained only large language models. And we use PaLM2 at that time. And we also try using different models as the optimizers, including PaLM model and the GPT model. So for all these approaches, we are starting from the initial instruction with let's solve the problem, which achieves an accuracy of around 61% for this GSM-AK task. And this is a pretty general purpose instruction. It is around 10% lower than the instruction let's think step by step. And if we look at the best LLM generated prompt among these, we can see that actually this instruction, take a deep breath and work on this problem step by step, achieves around 8% higher than this let's think step by step instruction. And actually, if we compare this performance to visual COT, it matches the performance reported in the PaLM2 paper, where the chain of thought exemplars are written by humans. So there are two things we can think about here. One is basically here we are seeing another way to basically achieve very competitive performance to visual COT without manually writing exemplars ourselves. Another perspective is that with this LLM-based prompt optimization, it doesn't only save us time so that we do not need to spend so much time to manually tune the prompts ourselves. But actually, when it comes up with new prompts, it also provides some sometimes surprising different angles. I can assume that, for example, turns take a deep breath. At least for me, if I'm trying to revise the prompt by myself, I won't feel that this phrase will be so helpful. But empirically, the large language model with this optimization loop, actually, it can somehow come up with this instruction that fits pretty well for this model. Note that in this LLM-based optimization process, actually this is not a real optimization in the sense that we do not have any training here. It is completely prompting only. So there's no guarantee that the model can just keep coming up with better and better prompts. But in practice, we find that actually this optimization curve holds for different models. So we can see that basically this with more optimization steps, which is basically these iterative prompting steps, the accuracy increases with more steps and then plateaus. So it looks pretty similar to the traditional optimization graphs. Okay, now let's go back to chain of thought. So from the methodology perspective, what does chain of thought really bring into LLM reasoning? Why is it so effective? If we think about it, chain-of-thought prompting is basically giving us a way to perform this variable computation of the thought process, which where this number of tokens used for a problem will be adapted to tasks of different difficulty levels. So if we think about standard prompting, basically for the same task, if the answer lengths are the same, then basically if we just provide the final answer directly, it basically means that we are forcing the model to use the same amount of time, same amount of inference time budget to solve each problem, regardless of its difficulty. But with this like chain of thought, basically it shows that for more complex questions, because it also requires more reasoning steps to solve the problem. Like for math problems, it might require more calculation steps. So basically with this chain of thought idea, it allows the model to basically also perform more reasoning steps in the token space so that it can better solve the test problems. And in the chain of thought paper, they also show that even if the difficulty of the problems is in exemplars are pretty simple math problems, but actually the same problem can also generalize to test problems that require much more reasoning steps. Then if we think about the high-level reasoning strategies, chain of thought also incorporates a lot of reasoning process that are very important for us humans to reason about difficult tasks, such as decomposition, planning, and etc. So if we want to further improve the model performance, and especially if we know what are some good guidelines on the reasoning strategies we need to use for a specific task, we can also explicitly instruct the LLM with the desired reasoning strategies for problem solving. So one idea to further push this decomposition strategy is called least to most prompting. And the goal of this approach is to achieve easy to hard generalization by explicitly telling the model what's the best practice to decompose the original problem. So on the slides, I'm showing this example for solving math problems. And basically in this original least to most prompting paper from my colleagues at Google DeepMind, it includes 2 stages. So in the first stage, it performs a problem reduction. Like given a math problem, it first reduces the problems into simpler sub-problems. So each sub-math problem can be easier to solve, requires fewer calculation steps. Then given these sub-questions, the model will be able to sequentially solve these sub-problems and combine the solutions to solve the original problem. The most impressive results from this work is that actually with this to most prompting design, it shows for the first time that we do not need to design the neural symbolic frameworks or requiring any program execution but it can still solve these compositional generalization benchmarks with a nearly perfect accuracy. So the results shown in their paper is on this SCAN benchmark. So SCAN is the synthetic data about translating programmatically generated natural language commands into action sequences. The most challenging part of this benchmark is about this length split. Basically, in their test splits, all the action sequences are longer than the training samples. So this makes it very challenging for the traditional sequence-to-sequence learning if we directly do this training on their training sets, and then on this length split, the test accuracy will be no more than 25% unless we apply some neural symbolic techniques. But then basically with this to most prompting, they show that if they use the latest models at that time, which is Code DaVinci 002, they're able to achieve nearly perfect test accuracy. At the same time, they only need to use 0.1% of the training samples as exemplars. So it is both more test efficient, data efficient to adapt to new tasks, and while also the performance is very competitive. Then in our follow-up work published at iClear last year, we further show that we can extend this least to most prompting idea to solve more complicated compositional generalization in the case of translating text to more realistic programming languages. Like here on the slides, I'm showing this example of translating natural language questions to SPARQL queries. So the main challenge here is that for more real-world languages, including natural language or programming languages, there are more complicated grammar rules, and also the vocabulary size is larger. This means that especially if we do not have a model with a super long context, then a single prompt will be no longer enough to cover all the grammar rules needed to solve the task. So actually, with this challenge, it shows one benefit of decomposition. By allowing the model to use different prompts for different reasoning stage, it also enables the model to use customized prompts for each subproblem or each subtask in the context of agent development. So here is an overview of our dynamic list to most prompting approach. So some details do not matter too much here, like how we do the decomposition. But the main new stage we add is this like so-called dynamic selection of the exemplars for each subproblem. So basically here, for each of the test sentence, we can discover those example questions with the most relevant grammar rules. So basically, we can assure that for each part of the sentence, we can always retrieve for the most useful grammar rules to solve the task, so that the model can have enough context to solve the problem. So on this compositional free-based question benchmark, the CFQ data set, again, we show that actually our dynamic list to most prompting approach outperforms all these baselines, where we need to train a model on the complete training set. And again, if we compare this dynamic list to most prompting with channel sort prompting and other prompting approaches, it also scales better when we increase this exemplar pool to generate these future examples. So far, we have talked about how we can instruct the model to solve the problem in some with some reasoning strategies indicated by the future exemplars. But if we think about it, we can assume that for different reasoning tasks, they can require very different reasoning structures, like there will be different ways to decompose the task and plan for each stage. At the same time, we might not want to annotate all these best practice for each type of task. Like again, we don't want to do this manual labeling of exemplars for every single problem. So in our self-discover work we published at NeurIPS last year, we basically instruct the model to compose task-specific reasoning structures without manually written demonstrations. So in practice, how we do it is that basically we will list a kind of tons of best practice of reasoning strategies, including channel sort reasoning, doing decomposition, doing some self-reflection, etc. Then given a new task, the model will think about how it can utilize the reasoning strategies that are best suited for the current task and compose the reasoning structure, follow it to solve the problem. And for evaluation, we also show that with this self-discover methodology, it outperforms chain of thought prompting and also other baselines on different benchmarks, including big bench hard reasoning task, math benchmark, and also some other benchmarks for social agent reasoning. So to summarize, in the first part, I first talk about chain of thought generation and the fundamental idea of allowing the model to perform variable computation to trigger the thought process. And this thought process can adapt to tasks of different difficulty levels. And we talk about how to improve the chain of thought performance at inference time. So in the original chain of thought paper, we talk about the future prompting idea with labeling of thoughts. We talk about instruction prompting to trigger this chain of thought generation. And also we talk about how we can instruct the large language model to automate the prompt design and discover better prompts by themselves. So notice that this best practice of interacting with large language models can evolve over time. Like for example, recently with these post-change large language models, you do not have to put exemplars for every single task for the model to learn how to do it. And also, for some models, for example, it is better for you to just provide very clear guidelines and instructions on what you want, and then hope the model can just follow your instructions. And some models prefer those interactive discussion, and some models might prefer just a very long and detailed instruction at once. But the principles of how to discover good prompting strategies for reasoning still hold here. Two very important criteria is that we want this approach to encourage the model to generate longer chain of thought for complex tasks. We want it to scale with different task difficulty. And also we need this like prompting technique to be able to support reasoning strategies required for the task. So now let's start the second part about perform search and selection from multiple candidates and increasing the ways to explore the solution space. So after we talk about the first part, what is missing so far? Yeah, I guess this question is not so hard since I already showed the outline of these slides. So basically, from first part, we can see that we should not limit the large language model to generate only one solution per problem, because the model can just have some mistakes in its single pass solution. Instead, we should allow the model to explore multiple branches, which will allow the large language model to recover from mistakes in a single generation. And there are two ways to basically increase the width of this solution exploration. One is that we can generate multiple candidate solutions per problem. Another is that at each step, we can allow the model to generate multiple potential next reasoning steps. It is not that hard to think that with this multiple sample generation, then the upper bound of the performance will be definitely higher because we allow the model to select an alternative, probably better solution. But the fundamental challenge for approaches along this line is that how to select the best response from multiple candidates. Because in the real world use case, we do not have an Oracle scholar at Inference-Time. So surely, for example, in a chat interface, we can just have the model generate multiple solutions and the user can pick whatever they want. Then this is kind of a best of selection case. But it will be more ideal if the model can just do this kind of process internally so that we do not have to review tons of solutions by ourselves to select what we want. So along the line of these ideas, I want to first talk about this self-consistency work from my colleagues at Google DeepMind. So if we look at this idea nowadays, we will find that this is an incredibly simple idea, but it is actually very effective, and it actually can improve performance a lot with all the different models. So let's say we want to also solve a math problem, and this time we allow the model to generate multiple responses. So basically, after we have all these responses, we still do not know which one is accurate. But here we have this consistency-based selection criterion. So basically, let's say for this math problem with a single number as the final answer, we will look at these three solutions. Two of them have the answer 18, and one of them have the answer 26. So basically, 18 is the most consistent answer. So we pick the response corresponding to this most frequently appeared answer. And note that here, one important thing is that this selection is only based on the final answer. It is not based on the reasoning passes. The model can come up with whatever reasoning passes it wants. So as long as they lead to the same final answer, we consider them to be all good. This is a pretty simple idea, but actually it boosts the performance across different models and benchmarks. And here in their paper, they also evaluate all the models available at that time. And especially on math problems, they show very significant performance improvement. Now let's talk about this scaling effect again with the self-consistency approach. So for the baseline here, in the curves, they compare with sample and rank baseline. This is actually a pretty natural baseline, which says that we can select the response with the highest log probability. So then here the assumption is that if the model gives higher probability to the current response, it should be more confident about it. But actually, if we look at these curves, we can see that self-consistency performance scales much better than probability-based ranking. So with more and more responses, up to 40 responses, self-consistency performance is still improving, but this sample and rank baseline has already stopped improving with around 10 responses already. But there is an exception. So the exception is that if we train the model to be a very good verifier for the task we care about, we might be able to kind of outperform this scaling curve with self-consistency. And we will talk about it later. Another very important factor that contributes to self-consistency success is that we need the model to generate very diverse responses to perform this consistency-based selection. So here, basically, in these results, they also compare with different baselines. So the beam search is actually a very classic search algorithm, in the NLP literature before the LLM area. So basically, the idea is that at each decoding step, we will keep the top k tokens with the highest probabilities. Then in the end, we will use the sentence with the highest overall probability. And then they also compare with these ensemble baselines, where they apply greedy decoding for among different variants of how you formulate the prompt, because earlier we mentioned that the LLMs are sensitive to different prompts. Also, they compare the performance to different ways to permute the exemplars orders in the prompt. So again, they show that self-consistency using sampling scales better with more samples. So the important factor here is that basically for the sampling method, it needs to ensure that the responses are very diverse. So we can do this sampling with a high temperature, or we can perform nuclear sampling with by setting the parameters in the right way to enforce this diversity, etc. One analysis from this work is actually pretty interesting. It is related to model calibration. So this is about actually how does this consistency-based selection improve the model performance? What does it mean when the model is for a given task, the model can come up with a more consistent response? So here basically they show this curve to show the correlation between the accuracy and consistency. So here basically we can see that if for those sample responses, if more of them lead to the same final answer, this means that this consistency percentage is higher. Then there are two conclusions we can see from here. One is that this large language model is more certain with its final predicted conclusion, even if they are coming up with the same conclusion with different reasoning passes. And empirically, we see that this aggregated solution for these more consistent responses can be more likely to be accurate. The final solution can just be the right one for the original test problem. So this can also explain why this consistency can be a very simple but very powerful criterion to select the final solution. So in the self-consistency paper, they demonstrate this approach on those text-based reasoning problems. And actually, this consistency-based selection approach is also very powerful for code generation. And in our AlphaCode work at Google DeepMind, basically this AlphaCode system itself is a pretty complicated one. It includes model training and inference-time techniques. But here I will mainly focus on this inference stage called filtering and clustering. And especially this clustering is basically tries to do this code selection based on the consistency on execution results. So let's first briefly discuss about the background, the problem setting of competitive programming. So basically, in a competitive programming problem, in the problem description, it will include a very long and complicated text to tell about the background story, about what we want for the problem, for the corresponding code. And then also includes a few improbable pairs as test cases. Then for the solution to be considered correct, the generated code needs to pass both the given test cases in the prompt, and also usually we will have some heard of test cases, and these test cases are typically of larger scale, and they will be more difficult than these example test cases, and they will cover some corner cases. So since we already have some improbable examples, we can filter the programs that fail the given test cases already. But for the remaining programs, they might still fail on the heard of test cases. Like for those of you who have participated in these coding contests, you might feel the same way. You feel that your code is great, but it just failed on some mysterious hold-down test cases, and you didn't get the score you want. So basically, for this for the AlphaCode system, the way we do it is that we will train another model to generate new test inputs for these test problems. Then we will execute those like sample programs on all these like model generated inputs, and then we cluster all programs with the same outputs together. The assumption here is basically if we have the model to generate like enough number of test inputs, and also they are diverse and of higher quality, then actually we can assume that all programs in the same cluster are semantically equivalent because they lead to the same execution results. And then finally, we sample one program from each of the 10 largest clusters. In our evaluation, we show that this clustering provides additional performance gain compared to the filter-only method. But clearly, there's still a gap from the oracle selection because there's still no guarantee that the consistent response will be just the best one out of the candidate pools. Now let's revisit this self-consistency decoding pipeline. So one limitation here is that for the original self-consistency, we need an answer extraction process so that we can do this aggregation among the candidate responses. So if you want to apply this consistency-based decoding to broader use cases, the natural next question is how we can do it for free-form generation, where it is not that natural to have this aggregation and answer extraction process. So this is what we want to achieve with our work on universal self-consistency. The idea is that instead of having this answer extraction process, we ask the large language model to perform consistency-based selection. So specifically, we threw an instruction to the model asking it to select the most consistent response based on the majority consensus, and also it needs to take a look at all these candidate responses. So the intuition here is that clearly we know that it will be hard for the model to judge the answer correctness by itself, but consistency should be a simpler criterion to measure. Then empirically, we also evaluate this universal self-consistency method for different applications. So for those free-form generation problems, like summarization and question answering, with long factual final answers, we see that the universal self-consistency also still can improve over the baselines, where the original self-consistency is not directly applicable. And on math reasoning and coding problems where we can apply this original self-consistency idea, actually universal self-consistency can match its performance without the requirement of performing this answer extraction and code execution. And notice here, clearly this universal self-consistency performance is bounded by the long context capability. So at that time, we are using an earlier model, which is not super great at long context reasoning. So we can see that when we include more responses in the prompt, the performance might not go up as well as the original self-consistency. But we can see that with the recent development of long context models, this will allow such kind of a model-based selection approach to scale more with more responses. And also in practice, for most tasks, it can be well solved within, let's say, 10 responses in a candidate pool. So this will still showcase this usability of this model-based consistency selection. Previously, we talked about for the model-based selection using the log probability from the original model. This approach of ranking doesn't scale better than the consistency-based selection. So to improve further over this consistency-based selection, one idea is that we can train a large language model as the ranker, and we hope that at least this ranker can perform better than this simple consistency criterion, and actually it can have some kind of sense of which responses are more likely to be accurate. So here on the slides, I'm showing this kind of diagram from the original OpenAI paper, which introduced the GSM-AK dataset, and also they demonstrate this method of how to train a verifier to basically judge the correctness of the math solution. And also later on, they have this follow-up paper called Let's Verify Step by Step. So in total, basically for this line of LLM-based ranking works, there are two ways to basically design the LLM-based method to judge the answer quality. The first way is the most in the initial and the most standard approach, which is called outcome supervised reward model. Basically, it will verify the correctness at the solution level. like given a math problem, the solution, the model will tell you whether the solution is correct or not. Another approach introduced in this Let's Verify step-by-step paper is called process supervised reward model. So the idea is that instead of verifying at the solution space, we can also verify at the step level. We can see whether each step is accurate. So in their work, basically they show that this process supervised reward model actually scales better with more samples compared to this outcome-based reward model and also this majority voting baseline. But clearly here, the performance will be highly dependent on the verifier quality. And also the same verifier might not generalize across tasks, because we know that this consistency-based criteria is very simple and actually can be directly applied to many tasks. But for these ranker models, you need to design a good training strategy and also design a good training data so that it can really work across different domains you care about. So far, we have talked about response selection only at the solution level. So we only perform this selection after the full responses are generated. But assuming that we have a very good stepwise scaler, then actually this solution-based response selection is kind of a waste of using this stepwise scaler, because actually we can do more with such kind of a more powerful and more fine-grained verifier. So if we already have this good stepwise scaler function, then actually we can perform this a tree search with large language model, where basically instead of waiting until the solution becomes complete, during the search process, we can just we can prioritize those exploration of partial solutions at the step level, and we can explore those more promising steps before exploring other paths. So on the slides, I'm showing this diagram from the Tree of Thought prompting paper. So from this illustration, you can clearly see what are the differences of different prompting methods. Chain of thought prompting is basically a chain. This self-consistency method is multiple parallel chains. And then for this tree of thought, basically at each step, it can have multiple branches to explore the next step. And you don't have to complete all these passes until the end. So here I will show this how we can apply this tree of thought idea with a simple example of game of 24. So basically at each step, there are two important stages we want to do. One is called thought generation. Basically, this step will we will prompt the large language model to propose possible next thinking steps. Like in the game of 24, these thinking steps are pretty simple in format. You just need to select the two numbers to perform this calculation. Then there's another stage called thought evaluation, where again here we can prompt the large language model to evaluate how promising the current state is. Like for the game of 24, you need to decide whether it is possible to reach the final number of 24 after all the manipulations. So previously we showed how we can show how we can do this evaluation at the step level. So it will determine the quality of each individual step. But related to our previous consistency-based selection discussion, for this scoring function, we can also think about it as a way to just select the best state among the candidates. We don't need to just have the model to make this decision at the point level. So the idea is that basically we can ask the large language model to select the best responses among all these possible next steps. And then basically we can also do this voting multiple times, since all this selection here is based on large language model sampling. Then with all these different votes, the model can finally select the majority vote as the final choice to proceed. Here for the results, I'm showing this game of 24 evaluation, and in the original paper, they also show some other benchmarks. So we can see that with tree of thought using breadth first search, it scales better than the standard prompting and chain of thought with respect to token budget. And going further, clearly we can integrate some more advanced search algorithms. Like in this original tree of thought paper, they use the most basic BFS and DFS algorithms. But in the later on, we also see some like papers which are coming up with these like multi-color tree search methods, and some MOOCs are also trying to train a separate evaluation function instead of just prompting the model. Again, here the important consideration is that we need to design a good language model and prompting scheme so that it can be effective for self-evaluation. So to summarize, in this second part, I show that we can further scale this inference time compute by sampling multiple branches in the solution space. And we talk about consistency-based selection, which is a pretty simple but effective and general principle. We talk about this self-consistency, where we can marginalize out reasoning passes and do the selection based on the final answer. And for code generation, we can also do this re-ranking based on execution consistency. When this large language model self-evaluation works well so that it can really judge the quality of partial solutions or judge the quality at the step level, we can also apply this like search method. And in this case, sometimes it will scale better. And also you can reduce the token cost because it can already eliminate those non-promising passes during the meantime. So finally, I will talk about iterative cell improvements, which will try to increase the depth to reach the final solution. So even with the most recent like advanced models, including those reasoning models, we can see that they can achieve pretty amazing like numbers on those competitive like and challenging benchmarks for solving hard math and coding questions, but they can still sometimes make pretty obvious mistakes, and people are keeping complaining about it. But if we think about us as humans, we also tend to make sometimes pretty trivial mistakes at first thought. So previously, we talked about we can sample multiple solutions to help us reduce these mistakes from a single prediction. But if we think about it again, it is actually a pretty suboptimal way to do this error correction. Because all these responses are generated in parallel, so we do not really learn from the past mistakes. We can just having the model generate the same wrong predictions again and again. So basically, in this part about inference time self-improvement, I will talk about techniques using large language models to iteratively improve its own response for the given task. And also, this will align better with us humans, like an error correction process. So the first papers about these ideas include this like reflection and self-refine. So basically, in this process, there are also like two important steps after generating each solution. So basically, after the model generates the solution, the model will also generate some feedback based on what it observes. In this step, it can use those external evaluation when available. So for example, in the original reflection paper, they focus more on this agentic setup, where basically the LLM as the agent will propose actions to the environment, and the environment will basically gives the model some kind of like changes of the observations. So this will be external signal to tell the model whether the current step is promising. Then based on this like model generated reflection feedback and also these external observations, then this large language model will refine its like output to revise its next prediction step, given both these internal and external signals. In this reflection paper, they basically show that this self-reflection and self-refinement works pretty well, especially when we can have a scheme so that basically the model can utilize pretty high quality evaluation, or when the external signals are very reliable. So for example, in the case of ALF word, it is basically an agent like a navigation task. So there will be clear signals about observations at each step. And they also evaluate on their approach on hotspot QA, but they kind of repurpose this like a QA task into an agent environment in the sense that after the model generates the solution, they assume that this environment will give a signal about whether the current solution is correct or not. Then this is why you can keep seeing this like improvement with more trials. We will revisit this assumption later. And if we think about this like self-improvement loop for applications, then code generation is actually a pretty natural use case. Because for when we are writing code, for us, for example, we also like debug our code better within an IDE, and we do not just write the code and we stop. We actually really rely on this like interactive loop when we are trying to investigate all these code execution results and see whether it makes sense and also which parts we should revise later. And this is also like this one fundamental idea of the recent coding agents. So in our paper, self-debugging, we also like do a deeper dive into what kind of feedback formats will be helpful for the model to better correct its own mistakes. So for example, the most like a simple feedback message is basically a short universal information about whether the current code is correct or not without more information. And then for unit test feedback, basically we also include the execution results, like whether the current unit test has passed or whether there are any runtime errors. Then for code explanation, basically at each step, we also ask the model to self-generate some line-by-line explanation of the implementation in natural language. So this idea is that kind of motivated by human-robot duck debugging, trying to ask the model to see like what it's trying to do in the code. And finally, in the trace feedback, basically we ask the model to perform some line-by-line simulation of the execution trace by itself. This is also one way of debugging by human programmers. Empirically, we evaluated the latest large language models at the time of paper publication last year. So basically, we can see that with this self-debugging loop, it consistently improves performance across different large language models of different capabilities. And also, if we give more informative feedback, it can further improve the debugging performance. Now let's go back to this like self-correction for question answering tasks. Previously, we talked about these results of hot-pot QA, and also in some other works, it also shows this improvement of self-correction on other reasoning tasks like math problem solving. But all of this like significant improvement comes from the assumption with an Oracle verifier. But in practice, this Oracle verifier will not be available in many scenarios, especially in the case of solving reasoning problems. You can imagine that when you are taking a math test, you don't really have the official solution at hand. Otherwise, it will be just trivial for you to finish the exam. So basically, the question here we want to study is, how do these large language models perform if we do not give the model such very like explicit and accurate external feedback about the response correctness? So in our paper published last year at iClear called Large Language Models Cannot Self-Correct Reasoning Yet, we actually show some negative results from this study. So we compare with this Oracle like baseline, where we basically utilize the ground truth answer for correction, and same as previous works, we show this huge improvement. Then we study the case of the real self-correction, where basically we do not allow the model to utilize any Oracle feedback. The model needs to judge the response correctness by themselves. Then these are the results we show in the bottom table. We can see that the main issue here is that because large language models can wrongly judge the correctness of its predictions, it often turns an originally correct solution into a wrong one. So this is why actually in this like self-correction without external evaluation, this process can lead to worse performance after each round. So with this study, one natural question is probably we didn't tune the feedback prompt well, so this is why it fails. So to address this question, we also design several variants of this feedback prompt. And notice that all these feedback prompts are pretty general. They are not like specifically tuned for one task. So we can see that if we just have this like simple general purpose feedback prompt, if we do not have any more like of the model training, then editing this feedback prompt indeed can affect the self-correction behavior. But this is more about adjusting the tendency for the model to keep the initial response. So in some cases, actually, this like feedback after the feedback prompt update, there's no much regression on the reasoning performance. But then in this case, this also doesn't help the model to improve over the initial performance. So previously we discussed about this comparison if we just do this self-correction over one initial response. And we further compare with another method where basically we do this self-correction among multiple responses. So for this, we compare with the multi-agent debate baseline. The idea is that we will have the model generate several responses in parallel once. Then we prompt the large language model to review these multiple responses and give an updated one. And for this multi-agent debate, we will compare with self-consistency. Recall that self-consistency is just completely generated solutions in parallel and select the response with the most common final answer. So in the previous multi-agent debate papers, they are showing some improvement over self-consistency, but we find that the major issue is that they do not have a very rigorous comparison in terms of the token budget. So actually, because in the multi-agent debate, each round for this specific experiment has 3 responses. But basically, if we keep the same number of response budgets, we will see that actually still self-consistency scales better than the multi-agent debate. Because at some point, this multi-agent debate performance stops improving, but with more responses, self-consistency performance is still improving on this GSM-AK math problem benchmark. So given all this discussion, then the question here is how we can best utilize the token budget by integrating all these different methods together. So the fundamental question is here, basically we need to understand how to balance the inference budget for generating multiple samples in parallel or sequentially. So actually, this is a pretty difficult question because it really depends on the task and the model. Basically, in essence, it's about whether the model for evaluation is good at self-reflection and correction for your specific task. So here I'm showing an example study from my colleagues at Google, where they are trying to basically in these specific experiments, they are trying to find the optimal way to scale this token budget to solve the math problems. So actually here they train a model which is supposed to be more specialized at correcting math solutions, and also basically here for the different difficulty level of problems, they study what's the optimal ratio to perform this parallel generation versus sequential generation. So I would say these concrete numbers will really vary a lot among different models, but basically here the overall conclusion is that for simple problems, actually the model can benefit more from self-correction because it knows more clear about whether the current solution is wrong and how it should revise. But for harder problems, actually there is better point in the middle about how much you should perform parallel generation and also this sequential refinement. And then with this kind of compute optimum factor for different task difficulty of problems, they show that this compute optimum curve can also scale better than this complete parallel generation. And when we think about inference time compute, another factor we should consider is about the model size. Because intuitively, with the same force budget, we can sample much more solutions from a lighter model. So if a more expensive model does not perform much better than a cheaper model, then it will not be a very optimal way to do the inference by calling the more expensive model. So basically, from this empirical study from the paper inference scaling loss, so basically, again, they will show that with the optimal model with different inference budget can be different. Like when you have a smaller inference time budget, maybe you want to rely more on the lighter models. But basically, when you have more budget, probably you can utilize the more expensive models, which can probably give you some boost on those very challenging problems. Where with the smaller models, it might it will be very hard to come up with the final solution anyway. So basically, in this lecture, we have covered different ways to perform this inference time scaling with the more token budget. So we talk about the basic prompting techniques, about this search and selection to increase the width of exploring the solution space. And also we talk about iterative self-improvement. And again, the best practice to interact with a large language model should be adapted according to its capabilities. So you really need to consider the underlying model capability and also the task in your hand to think about how you can best combine all these different techniques and design a more efficient and effective paradigm for your task. And finally, I also want to talk about the general principle of how to design effective reasoning techniques. And this actually will be helpful for both inference time techniques and training time techniques. So I guess many of you might have heard about this beta lesson from Richard Sutton, but if not, I highly encourage you to read this web page. Actually, I would say this is a very important guideline for many of the modern machine learning works, and especially with the recent development of large language models and reasoning techniques. So this article itself has a lot of text, but I will quote some most interesting text in my opinion here. So basically, what we really want to develop as a method is basically laws that can continue to scale with increased computation. And when we want to improve the AI agents, we want to basically teach the model to discover what we can't, not which content what we have discovered. So it is more about having some methods so that we can kind of trigger the model to know how it can keep improving itself and how to have the right way to perform the reasoning. So this is the end of this lecture. Thanks for listening.